Again, welcome to those who are not live with us, and we have quite a few of you guys. Today is March the 15th. It's 12 p.m. This is the lecture. I must say a couple of things. First of all, there is an issue with Zoom, big time, okay? I'm experiencing delays. As a matter of fact, earlier there was a major disruption in a previous class where for some reason, basically, it stayed frozen. The voice was frozen. However, the writing, the screen, the video was still ongoing. So I didn't know. So I really had to reboot my Zoom and restart it again. Please, if you notice that, please come back, okay? If you notice that there is some sort of a frozen, I don't really end the class until the class ends. So if you think that probably just midway, for some reason, Zoom stopped from working, please come back to it, okay? So that we continue the class. So that's really the problem that I'm running into. The other problem also has to do with Zoom. And that problem is also, even after the class is over, the recording is taking a long time for it to be made available for me to make it available for you guys. So it's really ideal that you guys attend the class live. So if you really have to be not in live in class, that's for online stuff now that we can't really do much about it. You still have to watch the recording when it's available and answer all the prompts related to it, okay? We are one day behind in schedule, and that's fine. I'm not complaining, but just to let you know where we stand in terms of overall picture. I'm hoping still that we're not going to miss the exam, which is going to be on on-campus exam. So we really have to do that and make sure that we're ready for it. Okay. And there was something else that I have been saying, and this is not really an announcement or anything else. It's just something that I said when we started the class, that this is really, we are supposed to basically solve for F equals to MA, and then for some reason, now why is it not showing anything? That's not good, man. Hold on. Let me see if I can click out of it and click back in it. Now it works, sure. Okay. Okay, so basically, I know we said in the beginning, this is really the deal. Okay. And our objective was to find F by finding E, basically. And if we somehow can find E, we're in business. Then we found three ways of finding E, basically. The first one is just a brute force integration and summation and calculations. That works in some cases. Then we found the case when there is symmetry, we can use Gauss's law. And that works too, provided that there is symmetry. Otherwise, the problem is as hard as the brute problem, okay, brute force problem. Then there is a third option, which is to basically, instead of calculating the vector E and dealing with three components of which, it's a good idea to find the vector V and then work your way backward in doing the derivation. Technically, and not always guaranteed also, especially in practical perspective, that derivation is easier than anything else, provided you can find V. But finding V itself requires an integration, a summation over all of the charges. So those are the three methods that we found. Here is a secret, okay? And I know I didn't say it in the beginning for the purpose because to connect with physics 4A. Honestly, we really don't care much about this expression in here. We will need it at some points, okay? Like the other day, for example, when we were doing the projectile, or a similarity with the projectile. So what we had plates. One of them has a distribution charge sigma, and the other one has the same distribution charge except it's a negative sigma over an area. And we found that basically there is a potential. I can take V to be 0 here, and V is some number in here, which turned out to be just basically E times D, where D is this separation between the two plates, okay? And E, for this case, we argued that it's 0 everywhere except between the plates, which is sigma over epsilon naught times D. So this is the whole overall difference in potential, if you wish. This is between the upper plate and the lower plate, between UL, if you want to call it UL, upper plate and lower plate, because the upper plate is a positive and the lower plate is negative. So the upper plate is higher potential than the lower plate. As a matter of fact, if I go straight and don't go all the way there, the potential in here is increasing with height. And this is basically, turns out to be the potential is just a function of how high we are from the reference point, which we took in this case to being the lower plate, okay? So the analogy there was that if I bring a positive charge in here and don't give it an initial velocity, actually, it's going to fall, okay, provided it's positive charge. And this is similar to gravity, because I can apply F equal to ma in this case and say that ma is equal to the force in this case, which is just the electric field times q times sigma over epsilon naught. And the acceleration from here is clearly constant, pointing toward the bottom. So it's going to be q over m times sigma over epsilon naught, okay? So if this were a proton, it's going to fall like gravity. So we applied F equals to ma there. As a matter of fact, if the charge was negative, then it's going to still do the same thing, except the acceleration is going to be, as a matter of fact, I did something wrong in here in the signs, because I took this one to be positive. Therefore, the acceleration is actually negative in the case of the proton. In the case of the electron, for example, the acceleration is going to be the same magnitude because the charge is the same, but the masses are different. So it's going to be the Q of the electron divided by the mass of the electron times sigma over epsilon naught. And still, it's going to fall because it has a lower mass. It's going to accelerate faster, going to have a higher acceleration. So it's going to gain more velocities. In either case, if both of them have initial velocity in this way, it's going to be a projectile motion this way or a projectile motion this way, because the electron will see itself accelerated faster than that of the proton, okay? So the bottom line is, I mean, if you think of ions in general, so they have their masses, which is well defined. Sodium, for example, ion, so it's going to fall down. Chlorine is going to go up, and so on and so forth. So this is, in a sense, we use F equals to ma to understand this motion, and that's fine, okay? But most of the times, honestly, we're not going to be dealing with this expression unless we actually need it. For example, when we're going to come to a point where we're going to do a cyclotron, which is a nuclear accelerator used to accelerate elementary particles, we're going to use a version of F equals to ma, but it's really the conservation of energy. So we're going to say the kinetic energy is equal to the potential energy that the system basically lost during the process, okay? Because it's accelerated by an electric field, and then the particle will gain more and more speed until it emerges with tremendous speed. We're going to probably use it also for the betatron, which is a different kind of accelerator that uses actually a different way of confining the charge and then accelerating it. But that's later on when we get into magnetism. Again, we're going to probably use F equals to ma there full-fledged. We will find difficulty using F equals to ma at that problem in a sense that it doesn't work, because we will find velocity is greater than the velocity of light. In that case, we say, okay, F equals to ma is not going to be applicable to us. We're going to invoke basic relativity. I don't know if we're actually going to do this, but this is a typical example where we invoke, you don't really need to know a lot of relativity. All you need to know is how the momentum is connected to the mass and the velocity. And we use that to find a better expression for the velocity. Otherwise, the betatron will accelerate the particles so high. So this is the stuff that I'm telling you that F equals to ma, the context with it. So don't hold me to this statement that we have to always come back to this expression and use it, because most likely we are not. As a matter of fact, today we're going to find a device, and that device will have applications in electricity. So we're diverting away from that idea, if you wish, okay? Hopefully this is clear in terms of how this course is moving. So here is the picture that I just was drawing again. So I have a sigma in here, chart, per unit area. I have a negative sigma again, per unit area. The electric field between them, if you guys remember, was sigma over epsilon naught. This is 0, this is 0. That is the electric field. The potential in here, the difference in potential that we found, this is, we'll call it V plus, and this is V minus. The difference in potential, I'm going to just call it V, which is the how big is V minus V1 minus. Okay, again, this depends on the choice of where you put that end, basically, of the multimeter, okay? If you put it right in the smack in the, that's how we chose the constant, really, okay? Otherwise, what really matters is the difference, because if we choose it in here to be 0, and this, let's say, for example, in the first choice, this was 0 volt, and this was 10 volt. If we choose the 0 there, this will become negative 5 volt, and this will become positive 5 volt. In other words, when you choose the origin, we'll just change the numerical values in there, but it's not going to alter the difference between them. If you choose the origin in here, for example, to being 0, obviously if it's 0 in here, because we really cannot, everything is 0 everywhere in here, but let's hypothetically, okay, that it's 0 here, and in here, then, for example, we find it to be 7 volt. Then in this case, it's going to be 7 plus 10, which is 17. What matters still is the difference in potential, okay? What matters still is a difference in potential, okay? So this is really the whole point of this. What matters between these two plates is the difference in potential. Obviously, I have a charge in here. This distance is d. And this expression was equal to sigma over epsilon naught times d, okay? So this is the expression that we have found in there, okay? Let's get this thing organized a little bit. Let's write the difference in potential. This is the difference in potential, not the potential. Difference in potential. Sometimes you will hear me say potential, but please don't forget that we are saying implicitly the word difference in here is included all the time from this point on, okay? Like the problems we did from chapter 23, the idea was problem, I don't remember their numbers, but one of the problems basically had two spheres, metallic spheres. One has a charge Q and the other one has a negative charge Q. We also found the potential, the difference between them, between the negative, the one that has a negative Q, the one that inside has a positive Q and the one outside has a negative Q, so that the total charge was still 0. The electric field was 0 outside and 0 inside. The potential was constant outside and constant inside. They tell you to choose the potential at infinity to be 0. So it's still the potential there is 0. So that device is very much similar to this one. As a matter of fact, for those two spherical things, we found the potential. So for the spheres from, I don't remember the problem. I think it's in here still. Yeah, it's actually this problem. We found the difference in potential between the inner sphere of radius A and the outer sphere of radius B to be Q over 4 pi epsilon naught and this ratio of these numbers. And we found it actually for the coaxial cables. The difference in potential also is proportional, is equal to lambda over 2 pi epsilon naught, the ln of the ratio of the radii. So these results seem there is a consistency between them. So in this case, I'm going to change the value in here, rewrite the value if you wish. So I'm going to multiply the numerator and the denominator by A, the area that is, divided by A times epsilon naught divided by D. So basically, I rewrote this expression no more by multiplying by the area of this plate. And it's the area of this plate, okay? So both areas are the same. So if I multiply by A, what I'm getting at, I have sigma, which is the charge per unit area. But now I multiply by the entire area, which gives me Q now. This is Q that I sprinkled around the plates. I removed negative charges and put them on the other side until I am left with a positive charge Q on the top and negative charge Q on the bottom. So this Q, this A times sigma is indeed the whole charge, divided by this number, which I'm going to call C. So what C then stands for, which I'm going to call the capacitance, which is this ratio. D is a capacitance by definition, first of all. And it tells me the following. If I do a charge Q between two plates, we're doing the plates, it's fine, okay? If I were to build a charge Q, by removing charges, like I explained the process last time around, we're going to have a difference in potential. How much difference in potential in here will depend on the geometry of this device, okay? And will also depend on the medium, which is air in this case. That's why I have epsilon naught in here, okay? So that's all. So how much voltage I'm going to get at the end with the same number of coulombs will depend on that. So if I want to have more voltage, for example, all I need to do is make C smaller. How can I make C smaller? Either by making the area smaller or by making the distance big. But that's going to be a problem for me if I do that. You have to be very careful with that, because I may not be able to do that, because this approximation, the sigma over epsilon naught, relies on the fact that A is too big compared to D. Okay, so that's how I play. Or there is another way of getting epsilon naught smaller. You can't really do that. Most of the times you're tempted to increase this C. Okay, most of the times you really want to increase C. So that is basically how you want to have more charge, if you wish, enclosed for the same voltage. Okay, you don't want the voltage to be too high, as a matter of fact, in here, but you would want to put a lot of charge in there. So how much charge do you really have stored in there? Q is equal to CV. Okay, so if you want to have a lot of charge, put a lot of C. That's all. So that is what the capacitance stands for in this case. So it's how much charge can you put for the same voltage on a device. So in this case, again, increase epsilon or change the medium, make it, and that's most of the time what we do in here. We put a different medium with a different epsilon in there. Okay, we put what is known as a dielectric. Okay, because if you put that, as if effectively we're changing this values in here by reducing this distance. Basically, you print a material in here. I know I'm getting toward the end of the chapter by now, but you put a material in here that can be induced, where you can induce charges in it. So basically, in actuality, this is positive is going to induce immediately a negative in here, and the negative will induce a positive in here, and the separation between the two as if it has been reduced. Okay, this is how much separation between these two plates, because this dielectric will absorb that. Basically, this material is called a dielectric, and it's easy to polarize. It has to be an insulator, though, because you can't really do it with a conductor. So once you have that, you have induced charges on one side and the other, then in this case, as if you have changed this value, but actually what you did, you changed this value, okay? You made this epsilon. The theory behind it is that actually that's how you arrive to the new value for epsilon. So you could change epsilon. You could change the area. You can change the diameter. You can play with the material in between them, or basically the physical geometry of the object, okay? So this is basically how you're going to do this. Again, the units. C is measured in the units of the charge divided by the units of the voltage, okay? How much the difference in potential you have between them. This is a coulomb, this is volt. Remember I said the coulomb is equal to the it's in ampere times second, and I know we didn't define that, and we are, okay? This is actually the next chapter, how we define the coulomb and the relationship between them. And the volt is actually, if you want to, is that by definition, if you multiply, or I'm sorry. Remember, Q times V is an energy in joule, and Q divided by, so the volt is actually equal to joule divided by a coulomb. So a coulomb squared in here, and then you have a joule, which is a kilogram meter squared by second squared. So if you really care about its units, it's an ampere squared second to the power 4 divided by a kilogram meter squared. We get sick and tired of calling it this way. It's too long. I don't even remember this, honestly. And you really need to verify the units, okay? But we gave it a name, okay? We gave it a name, and the unit for the capacitor is actually a farad, okay? So again, if everything is in SI, mass is in kilogram, distance is in meters, time is second, currents in ampere. If everything is in SI, the unit for it is going to be naturally in farad. Okay, so this is not a fundamental unit, but a derived unit. If you care about what is it, you can derive it, as I tried to do it in here, ampere squared second to the power 4 kilogram meter squared, which all of the MKSA system in here units are attending it. But it's really a It's a derived unit, just like the Newton. Okay, it's not a fundamental unit, or the joule, which is not a fundamental unit, but rather it's a derived unit. Okay, same thing in here. Okay, so you can work your way through it and find exactly how it looks like. Okay, the point being in here is this is the unit for it. Most of the times, though, and I know I had some capacitors in here, and this is part of the lab that we're going to be doing today anyway. Not today, I'm sorry, on Wednesday. Most of the time, it's measured in microfarads. Okay, you don't find you don't find a farad. I mean, it's too big of a capacitor, because then it's too huge. When C is too huge, the charge will be too much. Okay, so you really don't want that. Most of the time, because the charge of the order of microcoulomb or nanocoulomb, that is actually the order of nanofarad, picofarad, also 10 to the negative 12 farads and things like that. So that is the order of magnitude of it. Most of the time, practically speaking, those are the numbers. In the lab, I think we can have a few hundred microfarads, but that's too big of a capacitor that we use for in the lab. 10 microfarads, something like this. So that is basically the values that we find in here. So this is the capacitors. I defined it in this context, but if you care to find it for the spheres from problem, which problem that is, I need to know what the problem was. So this is the other problem for that. So this is, I don't even remember the number for this one. And this is the two charges. Okay. One of them I think was 41 and the other one is 61, but it's fine, okay? From chapter 23, okay, for the two spheres. So you have an inner sphere and outer sphere. This is of radius A, this is of radius B. And it turns out in this case, the difference in voltage between this point and this one, which I am taking 0. So this is again, a difference in voltage, not specifically a voltage at a specific point, was equal to Q over, was there a 4 pi epsilon naught or was just 2 pi epsilon naught? I think it was a 4 pi epsilon naught. 4 pi epsilon naught divided by, again, 1 over RA minus RB, or 1 over A minus 1 over B, okay? So again, the capacitance in this case is going to be clearly equal to 4 pi epsilon naught divided by 1 over A minus 1 over B, okay? So again, it's defined by the geometry, basically the radii of this inner sphere and the outer sphere, and also by this medium between them, okay? It's similar. So the formula is still the same in here, absolutely the same thing. So V is still equal to Q over C, okay? And C is measured in the same units. It's still always the units of epsilon naught times distance. This one is also epsilon naught times distance, because this is distance squared divided by distance, that is distance, times epsilon naught. So the units match. How about the case of the two coaxial cables, the very long coaxial cables? In that case, we found, so basically you have an inner cable and outer cable. And again, the inner cable has a radius A and the outer cable has a radius B. We found the result to be Q over, no, I'm sorry, it was lambda over 2 pi epsilon naught times the ln in here of the ratio of the outer over the inner. So in this case, actually, you can multiply it again by L divided by L, where L is the length of the actual cables, okay? So in this case, it's going to be Q in this case, because lambda times L is the charge charge in the wire, divided by 2 pi epsilon naught times L, and divided by the ratio again of the ratio of the distances. In other words, in this case, 2, it's equal to Q over C, where C is equal to 2 pi epsilon naught times the length divided by this ln of this ratio of these two radii. Okay, again, the ratio of the radii also plays a role in here in this case, although this is a unitless number, but it's still how big the separation between the two is. That plays a role, because B over A tells you how big the separation is, and L tells you also how long the wire is. So again, it's these proper units. This has no units. ln of B over A has no units. But this is, again, a unit of the distance times the unit of epsilon naught. And again, it's going to be in microfarads, and we can use the same thing. So the point being in here is that you can find V for any geometry, as long as, I'm sorry, you can find C for any geometry, as long as you can use Gauss's law or any law you like to find V as a function of Q. Then in that case, whatever that ratio is the specific geometry for that object and the medium that is between it. So what determines the capacitance is capacitance. Two things. First of all, the geometry of the device. Number two, the medium between the plates of the device. You're very good with this one so far? Good? I can see comments when you guys are, when I'm in this sharing mode. So far, so good? Come on, guys. Yes, no, maybe. Okay. This one person is okay. Okay. I can't see the comments or anything that you guys see unless it's your names are on the top, then I can see if you are reacting or not. Okay. Okay. So here is the the points basically in a nutshell. If you have a device, material, usually conductor, okay? You have another one in here, next to one another. Okay, both of them are conductors, by the way. Doesn't matter what the geometry is at this point. You take charges. You borrow a charge, a negative charge from here. I'm sorry, from here. You leave it positive in here, and you dump it on the second part. And you take another one, and you dump it on in here. Take another charge, one charge at a time. Okay? Obviously, it becomes harder and harder as you move along because of the fact that it's already positively charged and you want to remove another negative charge from here. It's going to be hard because of this electrostatic force. By the way, if you remove one or two, they are going to change their locations in such a way the geometry stays at with the minimum possible location. Basically, this charge will move all the way here away from the other one because again, it's a conductor and it has to stay on the surface. So the same thing in here, because you already have a bunch of negative charges. If you try to bring another one, it's too crowded already. So it becomes harder and harder. The first charge becomes easy. And then as you move along in the process, it becomes harder and harder as you do that, okay? So let's say, for example, right now, this is of course, I'm going to have a voltage in this case, because this is at a lower charge. This is at a higher charge. This is lower potential in this case. So it's going to be some potential, which I can take 0 to be. I can choose the origin there. So this is a potential V. So I already have a potential. When I put already charge Q on this side, okay. So at this point in the process, I know the potential is equal to Q over C. So we're still doing this. So we are still in the process of building charges, okay? The next time I want to borrow a DQ charge from here. So I want to take a DQ charge. It's not easy. It's going to cost me energy to do that. As a matter of fact, the energy that is going to cost, or the work I need to do, because this is negative and that's positive. So if I want to, this is a negative charge, by the way, the one I'm moving, okay? If you think about it, you could do it the other way around too. You could move positive charges if in here in this process, if you think about it too. Similar. So if I want to move a positive charge in here, DQ, this is already too much charges already in here. And it costs you work. You have to really do work to do that. And the amount of work, if you want to call it work, is going to be equal to Q that you want to add times the potential already there. You guys understand the process? This is basically the potential energy times the Q. That is going to be the work that is needed to do this amount of work. Yes, makes sense? Because remember, we saw the other day that the potential energy is related to the actual difference in potential via this relationship. So what I'm doing in here is I already have a V existing in this geometry, okay? By just virtue of this process. But what I'm trying to say in here is that the more you do this, the harder it gets because of the fact that you already have a V there. You already have charges there. And you would want to put another positive charge there, it's going to be harder because you have to overcome the electrostatic force. And this is exactly the energy that it's going to cost you for the next dq charge. Obviously, it's going to cost you a dw amount of work. Okay, so this is the work, okay, that needs to be done. Yes? If you don't like the word work, you can use actually du only. That's how much potential energy you're building actually over time. Good? Okay, very good. So here is the idea. I started with zero charge. Zero charge. Meaning zero potential. Okay? When I started, this is initial. My goal is the following. I want to reach a goal where I have a Q charge. Obviously, the potential there is going to be given by the same expression. V is going to be Q over C. Okay? This is the final. This is my aim. And the way I described it is I am somewhere in between. I'm not there yet. Okay, I've been doing this process for a long time. I'm trying to build this charge from zero when I had no charge whatsoever to my ultimate goal where I will have a Q charge. So this is just a Q charge. This is transition value between the two ends. So what I really need to do is you need to sum through all of this energies to find how much really energy I'm building in here. You understand? So every time I put a tiny amount of charge, it requires me work, so I'm actually storing that energy inside this device. So this is really what we're saying in here. So how much energy overall? It's going to be just the sum of this whole process from 0 to Q over this amount of work that I'm adding. Makes sense, doesn't it? This expression. I start from 0 charge. My goal is to end up with dq charge. Every time I add a tiny amount of charge, it's going to cost me this much work from the previous stage, because the previous stage I've already put Q charge in here somewhere. So I caught it right somewhere in the middle. And at that point, I have Q over C potential, and I'm dragging that dq in here to the other end. Yes? So this makes sense then. Just the summation of all of these things. I want you guys to be present in here and to be present with your minds, because I really, okay, very good. So, okay, all I have to do now is sub the value of this dq that I have found, du that I have found, which is just dq times this potential. And this potential at this point, it's Q over C. So this is actually the integral from 0 to big Q of Q over C dq. C is a property of this device. C is the capacitance of this device, so it's constant. So the energy, the potential energy that is, stored in this device is going to be 1 over C, the integral from 0 to Q of Q dq. And what is this integral equal to? What is the integral of x dx?
X squared over 2.
Thank you very much. Have a nice day. That's great. So it's going to be q squared over 2c. So if I want to build the charge q in the capacitor in this device, the capacitor, now we're going to call it capacitor instead of calling it device. This is a capacitor, by the way, with a capacitance C. If I build the charge q in it, I actually have stored the energy in it, q squared over 2c. Where is that energy coming from? It's from me dragging all of those charges, okay, at this point. So that is basically what this device is. So it's a device. Yes, we defined it earlier last time when we spoke, and we said that it traps the electric field. And it does, because in every of these cases, the electric field is zero everywhere. And in here, it's not zero. In this device, the electric field also is zero here, and it's zero inside the conductor also here. But it's not zero here. And it's true also for the parallel plate capacitor, where the electric field outside, above and below, is zero. Here is zero. And in between, it's not zero. So the device traps the electric field, but also stores energy. So it's a good device to store energy in it too. So the energy stored in a capacitor is q squared over 2c at any point, okay? So it doesn't matter. So this is the final point, but any point you have a q, you have energy. So the fact that you're putting charges on capacitor, what you're actually doing, you're storing energy, which is good. I mean, the whole point in physics is for energy. If you don't do an energy if you don't solve your energy, you have no, you didn't do anything actually, okay? We're gonna derive a very important result in here. Let's go back to a parallel plate capacitor in here. So let's look at this expression again. So this is A. This is the same area A, by the way. And the distance between these two is D. Okay? So this has a charge sigma, of course. This has a negative charge sigma. And this has a potential 0. This has potential V. By the way, I could call it V1. And I could call it V2. And what matters in this case is V2 minus V1. That is the potential that matters in this case, okay? So there is a difference in potential between the two plates, really. So the energy stored, U, is going to be equal to 1/2. So there is a Q charge in here. There is a negative Q charge in here, is Q squared over C, okay? Let's write this expression a little bit more friendlier, in a friendlier fashion, okay? Remember, Q squared is A squared times sigma squared. And this term in here involves, so let me write this expression here. U is equal to 1/2 of A squared sigma squared. This is how we started with, really. And the capacitance is equal to, in this case, epsilon naught times the area divided by the distance, the separation between the two. So it's the area times epsilon naught divided by D, okay? The area and the area square cancel, and the 1 over D will go upstairs. So this is going to be written as 1/2 of A times D times sigma squared divided by epsilon naught. I'm going to multiply and divide by epsilon naught in the last expression. The reason why I'm doing that is because I know sigma over epsilon naught is the electric field in this case. Sigma over epsilon naught is really the electric field in this case. So that's why I'm trying to pull the electric field out in here to see how this energy is written in terms of the electric field. So U, this is in joules, by the way, the energy stored in joules, okay? is going to be equal to 1/2 times epsilon naught. This epsilon naught times sigma squared over epsilon naught squared, that is actually E squared. So I'm going to write E squared in here, times this area times this distance, or the separation between the two plates. Let's look at this geometry clearly in here and see what that means. This is the area. This is the area, the lower area. This is the upper area. And this is the distance between them. What is the area times the height?
The volume.
Absolutely. This is the volume of this space. Does everybody agree with Milo? Area times distance is just the height, and area times height in this case is just the volume. Yes or no? This is not a democracy, guys. You really have to either agree or say he's wrong. One of the two.
Oh, that makes sense.
Okay, very good. Thank you. At least we have confirmation of somebody else. Okay, so this area times the height is really nothing but the volume of the space between the volume of the space between the plates. Okay, and that's where the electric field is not zero either, because the electric field is zero everywhere except in between the plates. It's not zero. So what this device actually does for us, so let me define a new quantity now. The new quantity is called the energy density, by the way. U, lowercase u, is big U divided by the volume. So this is the energy density. And the units for it are in joules per cubic meter. How much energy do you have per cubic meter, really? That's really what this question is. So if you have a tiny space, you have a tiny amount of energy. If you have a big space, you have a lot of energy. That is really what this little u is referring to in this case. It's going to be equal to 1/2 of epsilon naught times E squared. This result is extremely important. Very. I'm going to pull a trump on you guys, okay? Very important. And then Mr. Trump does this. Can I have an amen for this expression? The energy density is proportional to the square of the electric field. And also the medium where we're looking for it. This is so that you don't forget, this is the item of discussion, okay? I want you to remember this expression. The energy density is 1/2, first of all, the square of the electric field times the permittivity of the medium. Permittivity, 2 T's, the medium.
What part of this goes in the discussion?
Goes in the discussion. I want you to really try to put it in your own words. I want you to show understanding. It's going to be part of this discussion for chapter 24. And I want you to really ponder about this idea because of the fact that, look, what happened in here? We started with this capacitor, yes, this parallel plate capacitor, but the geometry of the capacitor now is gone. So it's removed. So this statement is true all the time. So the fact that you have an electric field okay? If you have an electric field somewhere, you have a bundle of energy, okay? Regardless of where you're doing it. And that is in essence, how your cell phone receives signal. The tower sends an electromagnetic energy, and by the time it hits your antenna, the antenna picks up the electric field component of it. There is another component also that is going to come later on, and then takes the energy from it. That is how telecommunications happen. That is how our eyes actually see. It's really a very, very important result. This is half the story, though. The other half will come later on. Half the story. The other half will come later on, and this is basically why I'm saying this is very important. So the next time when we see this an expression like this one, I will remind you for March the 15th, because it's going to be a very similar expression. Here is the deal. Everywhere up to this point, you saw epsilon naught, it was always in the denominator. It was a tiny number, 10 to the negative whatever, except today in this expression, it came upstairs. Epsilon naught usually lives downstairs. When it came to the energy density, it moved to the first floor. Okay, so this is something that I want you to think about too. Epsilon naught, wherever we've dealt with up to this point, 1 over 4 pi epsilon naught, 1 over 2 epsilon naught, sigma over epsilon naught, something over epsilon naught. I don't know, anything that you can think of was divided by epsilon naught up to this point. This is the first time where epsilon naught now is actually in the numerator, not in the denominator. Okay, so this is kind of a different way of it. I want you to think about this point in here. Down the road, we're going to find the similar expression, identical, with something else called the mu naught, actually. Instead of permittivity, it's going to be called the permeability of the medium. And the permeability of the medium, you will see that it lives always in the numerator. Every time you see mu naught, it's going to be upstairs. When it came to an expression similar to this one, it's going to move downstairs. Okay, so there are parallels in here. There is kind of a one-to-one correspondence. So it's really something that I want you to ponder about this entire expression and what it means so far. Basically, if you have an electric field, you have energy. All you have to do is square it, which means also it's very important that its sign, the fact that it goes up and down, doesn't matter, because when you square it, it's going to be positive. So it doesn't matter which way it's pointing. It's like the velocity, for example. If you're moving one way or moving in the other direction, the velocity can cancel if you have two objects moving one way in the opposite direction. So the momentum will cancel. However, the kinetic energy will not, because kinetic energy is proportional to the square of the velocity, which is the speed. So whether you're going left or going north, you still have kinetic energy. This is identical to that expression. The electric field can be pointing in every which way, except when it comes to energy, when it comes to the energy density in this case, it doesn't matter. It's always there. It's always positive. And that is really the power of telecommunications. That is why you're enabled to make telecommunications. So don't forget, and it's a very, very big deal also for a lot of your problems on chapter 24, they will need this expression. For a straight out capacitor, it's Q squared over 2C. So a lot of your homework problems will rely on this idea too. So I'm hoping that you guys have had enough ample warning about this expression. It's for capacitor, it's Q squared over 2C. We took this expression actually and derived an expression that doesn't depend on the capacitor. It's true everywhere there is an electric field, okay? So this is the energy density though, because if you look at small volume, you have that much electric field in it, so you still have energy, albeit tiny, okay? If you look at a bigger volume where you have an electric field, and that's going to be a bigger contribution in there. As a matter of fact, the Earth is being bombarded by an electric field from every which way from the universe, especially from the sun, and that is actually where the solar energy is coming from to some extent. So it's not to some, to a lot of everything, okay? That's coming in the form of electric field, and the other half we're going to take later on. So this is half of the story. As I was saying, this is not the full story, okay? So this is half the picture. So it's like you're looking, you have a quarter and you're looking at one side of it. So later on, we're going to discover the other side for it too, okay? So this is why it's important. This expression is extremely important for you guys. So having an electric field, an E field, really means energy. That's it. And this is what says that. This is the expression that tells you that, okay? So now here is another point in here, and I think this is the item with which we're going to close this chapter, but it's very important to understand what's going on. First of all, in electrical circuits, the capacitor represented by this symbol. So this is the symbol of a capacitor. Usually we put the value of this capacitance like this, C. Sometimes you'll find it referenced like this one, okay? So it's the same thing, capacitor, okay? It doesn't matter what geometry you have. It doesn't matter how you made the capacitor. It could be actually cylindrical one, like the ones that you have most of the times in your electronics. What happened to my capacitors in here? Did anybody see them? Oh man, there is one in there, hold on. Do we have any other electrical device in here? I have an old video card in here, and there are a bunch of capacitors in here if you can see them, okay? So this is how they look like on devices like this ones, okay? It's an old video card from a computer. I was trying to, yeah, actually, yes, there are all capacitors in here, okay? Next to my finger. So that's how they look like actually in actuality. And they come in small and big sizes depending on what you want to do with them. Symbolically, this is how it's represented though in circuits, okay?
Is there any difference between the symbols?
It's just, honestly, it's really not relevant, okay? There is a variable capacitor, and if it's a variable capacitor, you will see this one in here, okay? And the variable capacitors are important in terms of tuning devices, especially, for example, in the old dial devices. What you have in there, you have a dial that you turn, and when you do, you change the area between the capacitance in here. So basically, think of it this way, okay? So you have an area like this, and another matching area on the other side, okay? So in the dial, so what you do in this case, if you rotate one plate against the other, you're changing this cross section between them, the contact surface between the two, okay? So, and that is the area. Remember, the area plays a role in here too, big time, in this expression for the capacitance. What was it? It's epsilon naught times the area divided by the distance between them. So it's epsilon naught times the area divided by the, so that is how the old devices, so that is a variable capacitor, and you will see that too. Obviously, any device that we're going to be discovering is, if you see the arrow like this one, that is variable, okay? Okay, and one important one that we're going to discover down the road is the resistance, which is called the potentiometer or rheostat, and that is the one that actually we have them in the lab where you can change actually the resistance in there, okay? So again, in terms of this two, not much, okay? Depending on conventions and things like that. There is another device that we actually need right now. It's called the battery. So the battery, the symbol for the battery has two basically ends. It has an anode and it has a cathode. So this is the anode and this is the cathode. So this is negative plate, this is a positive plate basically. So this is how the battery looks like. So what's the role of the battery in a circuit? The role of the battery in a circuit is to maintain a fixed voltage or difference in potential, whichever you want to call it. Down the road, we're going to have a name for this thing, for a battery. It's called the EMF, the electromotive difference, I mean force. Okay, so ignore this word for right now. We're going to find it down the road, okay? But for right now, the purpose of a battery is to maintain the voltage across its ends, okay? So if somehow one electron, if you close the loop somehow in here and you have a bunch of devices in here, okay? So if one electron moves and finds itself on the other side, the battery will drag it to the other side. That's it. That's its role. Okay, and you ask me how does it do it? Because now once the electron comes in here, it cancels one of the charges in here and stays neutral. And that's all that you want, is to neutralize charges. But the battery has chemical processes to move a charge from where it's supposed to be to where it's not supposed to be. It's supposed to be here, then the electron, but it drags it to where the negative charges are. It's already crowded there with charges. So the battery's role is always to do that. As a matter of fact, I already, when I was talking in here in terms of this model, trying to build charges, it's not feasible that you do it by hand, you remove electrons. That's not gonna work, okay? So you really have to do it with a battery. So that's the process that I was describing in here, and how to build charges and how to actually build energy in a capacitor was nothing but really, this is the guy who does it for you. It's the battery. So this is a symbol for the battery. So if you see something like this in a circuit, you know exactly what this is. This is the positive, and this is the negative. The leg in the positive is longer than the leg in the negative, and this is the battery. It's unlike the capacitor where the two legs are the same, and you really don't have any sign up front until you build charges in it. Okay, so let's think of the following scenario. And there is a third device that I need for right now, okay, called the switch. So this is a battery. The switch is like this. So this is a switch. It's really, we're getting into chapters 24 and 25 really are kind of crisscrossing each other. They really should be called one chapter because all of these ideas are common. We will need the resistor for chapter 25, but right now we're needing these ideas also for chapter 24 because of the fact that we need currents and charges moving and things like that. So once you close the circuit, the switch, this becomes a wire. Okay, all of these wires are conductor, by the way. These are conducting wires. Practically, they're made out of copper, which is one of the best conductors you have out there. So this is basically a switch. So those are the things that you will see for this chapter and big time in chapter 25 and also in 26, okay? Chapters 25, 24, 25, 24 bleeds into 25, 25 and 26 are also actually big time circuits. So here is the idea. If I take this capacitor and connect it with this capacitor, I call this configuration series. I have two capacitors that are in series, okay? This capacitor has a capacitance C1, and this capacitor has a capacitance of C2, okay? Obviously, if I start building charges in here, Q, in here, negative Q will be established. This wire is neutral. Initially, before building charges, it was neutral. So it better stay neutral. So if negative Q charge move to this side, a positive Q charge must be on this side too. And if a positive charge is on this side of this capacitor, a negative Q charge is in here too. So if you imagine with me that you have somehow a battery in this case that caused all of this mess, okay? And when you turn the switch into this position, now this is the picture that you have emerged in here, okay? Make sense? It's usually the area between the capacitors, the two capacitors that you have to be mindful of, okay? So this is the positive end of the battery. This is the negative end of the battery. When I close the switch, okay, provided I have closed the switch. So this is an S. This is the battery. The battery, the symbol for it is the letter E in this case for the EMF, for the voltage in it. So this is the volt. If it's 1.5 volts, it's 1.5 volts. End of the story, okay? Make sense? So if somehow a positive Q pile up on one side of this capacitor, first of all, a negative Q must be on the other side. The reason is because there is actually the battery in here. The battery needs to maintain its voltage, so it cannot lose positive Q in here without also taking a negative Q to the other side. Otherwise, there will be an imbalance in the voltage. Remember, by definition, the battery maintains its voltage. No matter what you do to it, it's going to retain that voltage. So you have a negative Q in there. But now you have a positive Q and a negative Q in here. And this wire in here, this is a capacitor. They have to move in such a way to balance one another. And this wire initially was neutral, has no charge in it. It needs to stay as, with no charge in it. Does everybody see the picture so far? You understand what's going on?
Yeah, makes sense.
Okay, so here is the deal. Thank you. I'm going to take this point. I'm going to call it point 2. You will see why. And I'm going to call this point 1. This point in between, I'm going to call it 3. The voltage in here, I'm going to call it V2. The voltage in here, I'm going to call it V3. The voltage in here, I'm going to call it V1. Obviously, think of heights, okay? This is the first floor. This is the second floor. This is the third floor, okay? The first floor, the second floor, and the third floor. If I want to know the height between the first and the third, oh man, I put the symbol. That's fine. So this is the third. This is, oh man, it's okay. Hopefully you guys see it, that the difference in potential between here and here is the sum of this difference in potential plus this difference in potential. Make sense? The difference in height between these 2 points, regardless of what their labels are, is the same difference, the sum of these 2, between here and there, and between here and there. Yes?
Yep.
Okay, so thank you. The difference in potential between end to end is V2 minus V1. V2 minus V1. And the difference between this one is like V2 minus V3 plus V3 minus V1. Basically, V2 minus V3 is this one. And V3 minus V1 is this one. This gives me the whole difference. If you have never heard of circuits, if you're just walking into this class, you have never seen this class before whatsoever, and you have no idea what we're talking about, you know this expression is true. If you have any basic training in algebra, you should know that this expression is true. All I did was subtract the potential in the middle and add the potential in the middle. That's it. And this stays the difference in potential overall. Make sense? Algebraically? Good?
Yep.
Okay, so far so good. This difference in potential in this case between V2 and V3 is actually this charge Q over C1. And this difference in potential between 3 and 2 is actually the same charge Q over C2. So this, simply I can write it as Q over C1 plus Q over C2. Okay, that's all I'm writing in here for this expression. This device looks like, it's not, okay, but it looks like this from the vantage point of the battery. So you still have a battery in here. You still have a switch in here. Oh man, can't get this. You still have a switch in here. You still have point 2 in here. You still have point 1 in here. And whatever going on in there, you have a charge on one side and a negative, the same charge on the other side. You have a positive charge on this side, and you have a negative Q on the other side. So in between them are just details for right now. So it looks like there is a capacitor in here, which I'm going to call C equivalent, in such a way that this is, as far as the battery is concerned, this is how it looks like to it. So what's going on? The details are this. But for the battery, it looks like it's just a big capacitance whose capacitor is just C equivalent, as if it's equivalent to the 2. In other words, get rid of this device and replace it with this one, and you're going to be in the same shape. You have a Q, in this case, divided by C equivalent. Okay? Obviously, the Q doesn't matter really. And then I say in this case, the capacitor, the equivalent capacitance is simply the sum of 1 over C1 plus 1 over C2. I just took 2 capacitors. What if I have 3? What if I have a dozen of them? It's the same thing. So this is how you add capacitors in series. Basically, in series, you take the inverse of all of the capacitances and you add them up, and what you end up with is the inverse of the capacitance of the equivalent capacitance. So if you ever see a circuit, and let's say, for example, this is 2 microfarad, this is 4 microfarad, and this is 8 microfarad, and you have them in the same branch of a circuit. So you say in this case, ignore this, I'm going to replace them by a new one. One capacitance only, all of these 3. And it is equal to the inverse of 1 over 2 plus 1 over 4 plus 1 over 8, and then the whole thing to the -1. Because remember, you're going to inverse the quantity because this is just 1 over C equivalent. So once you get 1 over C equivalent, you have to invert it to get the correct number. And don't please put microfarads when you're putting the algebra. You're going to restore it back at the end, and that's it. So in this case, the common denominator is 8. And in here, I have 4 plus 2 plus 1, the whole thing to the -1. So it's going to be 8 over 7 microfarad. OK? Note, the equivalent capacitance is less than any of them. The least capacitance in this case is the 2 microfarads. And the equivalent capacitance in this case is less than that, okay? So the equivalent capacitance in this case is less than the least, less than the smallest, okay? So this is, if I take capacitance and put them in series one next to one another, okay? End to end, basically. How about if I do the following? Take this capacitance, C1, and connect it end to end this way now to a battery. For convenience, we usually throw in a switch in here because we don't want things to start before us basically controlling this. So the switch is usually needed for this purpose, okay? So we have a battery in here. So we have a battery in here. And we want to do the same thing. So we have a voltage in here, which I'm going to call 2, and voltage, which I'm going to call 1. Here is the thing. The voltage from 1 to 2, or the difference in voltage between 1 and 2, you can go this route. Okay? Or you can go to this route. By the way, this is C2. I forgot to put C2 in here. So in either case, the voltage between 2 and 1, which is V2 minus V1, is simply equal to, this is the voltage across C1, which is Q. So I'm going to call it Q1 in here. I'm going to call it Q2 now in here. So this is negative Q1, and this is negative Q2. Okay? So this is going to be Q1 over C1, which is the same thing as Q2 over C2. However, there is another important concept in here. This Q1 and this Q2 must be borrowed from this side. So how much did we actually borrow? We borrowed Q. So Q must have traveled this way and split itself between these two capacitances. And then recombined in here to come back as a negative Q to the battery in here, so that basically everything stays the same. The battery maintains the voltage across its ends, so it cannot lose some charge on one side without compensating it from the other. Otherwise, we'll have a difference in potential that is not correct. So the charged Q that was drained from the battery, this is what we actually took from the battery. Must be Q1 plus Q2. Why? By conservation of charge. Okay, by conservation of charge, the charge must be the same. You cannot really lose. You cannot somehow borrow charge from some thin air or from a wire or something. It has to come from a battery. So, and that charge is exactly the sum of the two charges. So empowered with that, so I'm going to write this expression in here. Okay, so this charge Q is clearly equal to Q1. Q1 is C1 times the voltage. It's C1 times the voltage. By the way, this is the voltage across both of them, so I'm going to write it as V. Okay? And Q2 is C2 plus voltage, times voltage, I'm sorry. Same thing. Q2 is C2 times voltage. So if I plug in this expression, for me, for the battery's perspective, this is how things look like. Looks like, again, we have a switch in here. From this end to that end, we took a negative Q and we split it between Q1 and Q2, it doesn't matter. And we have a positive Q in here. And for it, whichever way you do it, you have a negative Q and positive Q. So you effectively have a C equivalent in here. So that this potential indifference in here again is equal to, or the charge is equal to C equivalent times the voltage. So this is actually C equivalent times the voltage. So cancel the voltage because now remove the battery if you wish. And the C equivalent will be the sum of all the C's. So C equivalent, by the way, this is called parallel. So if you connect them this way, they're in parallel, okay? Versus the other one, which is side by side, which is called the series. So now, having said that, then if I bring one capacitor with another one that is in parallel with another one, with a third one in present, and bring as many as you want, just you add them up. To go back into the initial example in there, so if I bring, for example, a 2 microfarad and put it in parallel with a 4 microfarad, and in parallel with another one, which is an 8 microfarad, the capacitance in here, as you might have guessed, will be the sum, which is higher than the biggest one. It's the opposite. So C equivalence in this case is going to be 8 plus 6, which is 14 microfarad. And this is, of course, is bigger than the biggest, okay? Bigger or larger, larger magnitude than the largest. It's the opposite, okay? So in series, it's smaller than the smallest, and in the parallel, it's larger than the largest. It's the opposite, okay? So this is all of the things that we're supposed to cover in this chapter. We have great ideas that was introduced. The biggest thing is this device, and you can, and we're going to do problems from this chapter to on Wednesday, okay, in the morning. The problems that at least so far. Problem 1, I know that probably you'll like that, okay? Problem 1, the reason why I want to do problem 1 because it's straight out basically application of numbers, which is something you really need to know how to do, okay? Then problem 51, problem 53, 57, and 59. There will be another problem, okay? I'm still thinking about it, but there will be another problem for sure. So I really want you to get a head start on these things in here. And yeah, probably another one involving the energy also, okay? Any questions for this chapter? No?
I was actually just looking at the book. Are we going to be doing anything with dielectrics, or are we just sticking to the capacitors?
Dielectrics, basically you're changing epsilon, and it's going to be part of the lab, okay? Where you're going to change the dielectric properties of the medium. So most of the times, It's going to change epsilon from epsilon to epsilon r, which is a good question actually. Let me write the capacitance at least in terms of dielectric. Okay.
Okay.
So for the capacitors of parallel plate capacitor, basically in the lab we used to have a very fun lab where you actually build your own capacitance. Okay. So this is how the capacitance for the parallel plates is going to be, instead of epsilon naught, it's going to be epsilon naught times the area divided by C, divided by D, I'm sorry, times epsilon R, okay? Where epsilon R is the relative capacitance, okay? Relative permittivity, okay, I'm sorry, of the medium. Okay, and you experiment with different dielectrics, the purpose of which is to really make it stronger and stronger. It has a lot of application in engineering, especially when you're dealing with devices and you're trying to control the capacitors in there. You will see down the road something similar, identical to ferromagnets, where you actually have the permeability of different magnets to increase the similar properties there too, okay? So we're going to come back to it. Honestly, in terms of problems, it doesn't make much difference other than, okay, we have a problem, we may have to do it actually, where you actually introduce in and out a material in there, and that would be problem 60. We may do problem 60, okay? That's going to have a variable, basically permittivity in there because the medium is changed in there. So probably problem 60, okay? But at this point, I'm trying to do something more with the energy, honestly. So, okay, once we have the basic ideas, then this should not be an issue there, okay? So when it comes to optics, and for some of you are sitting in physics 4C at least, when it comes to optics, epsilon R plays a major role. This is related to the index of refraction of the material, and that makes a big difference for refraction and things like that, for optical devices in general and things like this. So it is important, but probably not in this context for the capacitance, at least immediately, okay? Any other question? Okay, Wednesday morning at 9 o'clock, and I know the time has changed, 9 o'clock, 10 o'clock, and I'm sorry, we meet at 12, okay? We're going to do problems, and hopefully we do as many as we can. And I may have to trim them more because I really want to get the energy also involved, okay? And then we have a lab, okay? Now with the lab that's been postponed, now we're ready for it because all of these ideas can be explored on Wednesday for the lab. Okay, any other question? If you guys don't have any question, I'm going to stop the recording, and hopefully it's going to upload. This time it went a lot better than the morning in terms of the Zoom session. Did not freeze on us. So I will see you guys Wednesday. We stop the recording.